In the last video, I discussed about how do we use Kolmogorov-Smirnov test for the normality of the data, right? But one of the problem that method to use R directly was if the sample data are repeated, then it shows some warning message, right? Because it doesn't work well if some of the sample data are repeated to test the normality. But if you do manually, it is perfectly fine. The method that I mentioned perfectly fine. But when you want to do ks.test, then it works well for the distinct data points. But if the data points are repeated, it doesn't work very well. All right. So I'm not saying that it is 100% wrong, but I'm saying that it doesn't work well. That's the warning message says. So now I'm going to introduce another method, which is a very famous method we call Shapiro Wilk test, and I will show you both by how to do by manually and how to do by using R directly. Okay, so this test does not have any problem if the data points are repeated. Okay. So it is one of the most powerful tests for normality. Many statistical softwares include this test. This test uses weight value of the Shapiro Wilk tables. There is a different tables. You can find that table online. You can just type Shapiro Wilk table. Also, the critical values are found from a Shapiro Wilk table. So there is another table. You can type critical value for the Shapiro Wilk test. So the original Shapiro Wilk table is limited for sample size between 3 and 50, and there is a revised Shapiro Wilk table for the bigger sample sizes. The following are the steps for Shapiro Wilk test. So what you do, you write H0 and H1. So I want to pick this example and I want to do all these steps in the example all together. Okay. So suppose you have this data set. Okay, there are 15 data points there. And suppose you have this data set and you want to test if these data are coming from a normally distributed population or not. You want to test that. So and then you want to use alpha equals 0.05. So first step you do is write on H0 and H1. So H0 is the data are normally distributed, and this should be H1. Okay, H1 is the data are not normally distributed. Okay, that is H0 and H1. Then what you do is to find the test statistics, first you need to arrange the data and find X bar and S. What I did for that is I am doing that. So this is my data. So this is this is my data. Where is my data? Let me find out that. So 1.2, 1.6, the last one is 3.5. Yes. So this is the data. Okay, and then I sort the data. Okay. And then what I'm doing here is this is the sorted data 1.2, 1.6 and so on. So I wrote that sorted data here. Okay, the last one is 7.6. That's the last one. All right. So next, after you sort and find out the X bar and S. So we will need that X bar and S, but I'm using directly here to find out X. That X bar is used to find out sum of square. How do I find out sum of square? You do xi, the data minus mean square, and then you add them. Okay, see what I did? Sum of y minus mean of y square. So if I do that, what do I get is 54.35. That is the sum of square. You see that? The sum of square is 54.35 there. That is SS. So next what you do is for the given sample size, for the given sample size, use Shapiro Wilk table 1 to find the value of AIs. Look at this. This is a Shapiro Wilk table. You can find this online again. So it has given the coefficient A1, A2, A3 depending on the sample size. The sample size in our case is 15. So for this, this is A1, A2, A3, A4, A5, A6 and A7. You see that? So A1, A2, A3 and so on. These are the AI values, A1 through A7 values for this sample size. Okay, now after you find out that, what you need to do next is, see, this is the maximum value, this is the highest value, right? And this is the lowest value there. So what you need to do is you need to find out the difference between the highest and the lowest. X15 minus X1. This is the first value, this is the 15th value. So X15 minus X1, you get 6.4. Next, you do X14 minus X2. X14 minus X2 is 5. How do I do that? Look at this. y, because we denoted by y for that value. So this is y15 minus y1. So if I run this, you will get 6.4 here. You see that 6.4. Similarly, you can do y14 minus y2, right? So y14 minus y2. If you run this, you get 5. You see that 5.0, and so on. You find out for all those. But one of the things that it is mentioning here is, if there are even number of sample size, then you will have these AI's values will be that sample size divided by 2. If there are odd, then you will have sample size divided by 2 minus 1. You will have that many, because you see that. So so it is a sample size minus 1 divided by 2, not minus 1 separately. Sample size minus 1 divided by 2. In our case, there are 15 data, so 15 minus 1 divided by 2 will be 7, right? So there will be 7 of them there. So there will be 7 of that difference. Because, see, the biggest minus the smallest, second biggest minus second smallest, third biggest minus third smallest, and then 9 biggest minus this 7th smallest, right? And another one will be 8th minus 8th. Here, right? So x9 will be the, you can do 7 biggest minus 7th smallest. You can do that way too. Okay, but you can name that way. You can call that way. But the another will be x8 minus x8. So that will be ignored because that will be 0, right? So that's how we find out that difference. Now what you do next is you multiply a value times the difference. You see that? This times that is that. This times this is that. This times this is that. So you find out a times the difference. Okay, so after you find out a times the difference, what you do next is you do then calculate the test value as b square over ss. So b is a times difference, that is the b. Now what you do is you do b square over ss, right? So look at this. What is b square? B square is, b is that value, the sum of that. I should have written the sum, okay? This should be sum of ai times di. Sum of ai times di. That is the b value. That is the ss value, right? B is the sum of those. That is b. And this is the ss value. So what is w? W is b square over ss. If you do b square over ss, you will get 0.873965. This is b square over ss. That's how you find out b square over ss. Okay. Now, use Shapiro Wilk table. That is the p-value table. These are the p-values. Okay. These are the p-values here. These are the sample size. You see that for p-value is, if p-value is 0.02, then the w value, these are the w values here. These are the w values. These are the sample size, and this is the p-value. Okay. So look at this. For the sample size 15, if the p-value is 0.02, the w value is 0.85. Okay. If p-value is 0.05, then the w value is 0.88. You see that? But our w value is 0.87. Since the w value is between this and that, then your p-value must be between 0.02 and 0.05. You see that? It must be less than 0.05 and greater than 0.02, because our w value is between these two, meaning the p-value must be between these two numbers as well. Okay, so if you find out that, then you can think, I mean, you can, so what it says here is, if find the p-value for a test, interpolate if needed. So you need to interpolate if you want to, if that is lies, if the p-value lies between those two numbers, so it's 0.855 and then 0.881, then you need to interpolate and find out the p-value. We know that p-value lies between 0.02 and 0.05, but we don't know what exactly that p-value is. So we need to interpolate that, okay? And then you find out the p-value that way. So the p-value is 0.041883. That's what you get. Okay, 0.041883. So this p-value implies that since alpha is 0.05, so p-value is less than alpha, meaning we reject the null hypothesis. Okay, so we need to reject the null hypothesis, meaning that the data are not normally distributed. Okay, so let us do that. Let us do that Shapiro Wilk. I think it is missing some data there, 4 there, because there is 4, it is missing there. Okay, so let us find out that data and then Shapiro value. You see that the p-value here is a little bit smaller than the p-value that we got here. So 0.03. So still p-value is less than alpha, right? So p-value is less than alpha. You see that the w value, we got exactly the same w value. Very close. 0.87, 0.87, that is the w value. And p-value also close to our p-value here, right? So that is 0.03872. You can do that directly using Shapiro.test. So although there 1.9 is repeated, so there is no problem. It doesn't say any warning sign there, right? So this is what you got. So from here you see that we reject the null hypothesis. So if you are curious, what would have happened if we use the Shapiro Wilk test from that data one that we were doing previously in the last video? If you do that, let me show you that how it shows. Shapiro Wilk test. So we got p-value is 0.07, which is greater than alpha. So we do not reject the null hypothesis, meaning this data basically is normally distributed. Okay. So if you want to see how is this the data, because when we did this one, we got p-value is less than alpha, right? For this problem, for this example I just did here. And then let us see how the QQ norm look like. Okay, so QQ norm and then X. If you do that, how that look like? QQ norm X. See, it is a little bit. And then if you do the QQ line, and then X. If you do that, you see that the line is a little bit. And then let us do color equals to 2. What would it do? So red line, right? You see that it is like a little bit not on a straight line. So you can kind of guess, but it is not like 100% perfect. The QQ plot is not 100% perfect. So the p-value method, that is Shapiro Wilk test, is the best method to test the normality. Okay, guys. All right. So so this is how you do that. In the next video, I will discuss about how do we what should we do if the normality test is failed. What should we do next to test the because most of our method needs the normality of the population, right? So if you get normality is violated, and then you may want to use different method for the normality. If all of those methods fails, what should we do to show the normality of the population? That is the next thing that I'm going to do. Okay, guys.